Well, good morning. I've only got my reading glasses with me today, so I can't see you. So if you're making rude hand signs, make them as large scale as you can. Anyhow, yesterday, before getting into lecture 2, yesterday I touched on issues of scales of change, of regionality, regional changes, and of global kind of, if not identity, at least global underlying patterns. And these phenomena have encouraged us to look at archaeological monuments and archaeological phenomena as if they are evolutionary creatures. Now, any evolutionary scheme, it doesn't matter whether it's Darwinian or Lamarckian or any other kind of evolutionary scheme, really needs two critical things. It needs a mechanism that generates change, and then it needs usually a separate mechanism that consolidates favorable change and eliminates or ignores the rest. Hence my comment, for which I've been slightly taken to task, that buildings don't bonk. We cannot imagine that buildings can vary by virtue of interbreeding, because they don't breed, guys. Hence also, I think, or somewhere in the background of that is Gordon Berkeley's concern that national archaeologies don't work, and so we should reduce to regional archaeologies, but at the same time not lose sight of the overall similarities that create these classifications for us. And today, in the next 2 lectures, you'll see that I return to that issue because I think it's central to how we frame and therefore how we consequently understand the archaeologies that we propose. So let's go to it. In this lecture, I'm going to explore the nature of chambered cairns, employing some of the concepts from lecture 1, but the topic will run on into lecture 3 as well. I want to talk about the mechanics of chambered cairns first, so that you'll understand some of the configurations of chambered cairns later. Let's start with loose material. Particulate material dropped from a point, like if you took a handful of sand and dropped it onto a flat surface, they'll form a cone that's characteristic of the material. It's influenced by the grain size, surface tension, wettability, and other factors of the material. The angle at the foot of the cone is the repose angle, and in the round we have the repose cone. And this is the configuration to which nature wants the material to go. Gravity wants it to take that form and no other form. Now, so bear that in mind. Principle 1. A rectilinear tank filled with water exerts pressure on all of its vertical faces. In fact, the force operates at a point in the middle of a face and 2/3 of the way down from the free surface of the water. You can, of course, calculate this hydrostatic pressure, as it's called, for any shape of tank. It doesn't have to be rectilinear. When we're dealing with soil, which is being revetted, or stone for that matter, which is being revetted by a wall face, it all becomes interestingly more difficult. But it's well understood. The principles behind it are reasonably well understood for most cases. And we have now fairly cut and paste formulaic means of calculating the stresses and strains on a revetment wall. In prehistory, of course, people had to acquire that information or that understanding by experience. With masonry, locally unresolved forces, if you look at the left-hand column first, there's a bunch of stones at the top. I've reduced them to a skeletal diagram and attached forces that are nominally or notionally operating in this way. Within a large body of loose stone, occasionally a stone shifts. Let's not worry too much about how and why it shifts, but it does, and that alters the configuration of forces. Those forces can be reduced to vertical and horizontal forces. The vertical forces we don't care about because the Earth is not going to give way. The horizontal forces, on the other hand, want to push the material outwards, and they are a problem, and we need to take cognizance of these so-called unresolved lateral forces. Forces are resolved if they're equal and opposite, and they just stop, nothing happens. But if they're unresolved, they move, and that movement is to the detriment of a dry stone-built structure. I put this in just to add a little flavor to the randomness of it all. This is a wall built in polycarbonate, which when you shine light through it, polarized light through it from behind, gives different color bands in proportion to the amount of strain that the polycarbonate block is experiencing at the time. And there are weights at the top there of both of these displays. And the strain that they impose on the structure can be calculated, can be calibrated from the colors. But what's also interesting is that you can see that there are islands of unstressed material in the middle of this cascade of strain. Keep that in mind, for later on we will talk about something called crack swarms when we're talking about brocks, less common with chambered cairns. Now, we said originally that things have a natural angle of repose. And that being the case, loose stone should take, I guess, that kind of form, where it's been stripped away very greatly, as in this Shetland cairn. It can be even flatter still. But many cairns are very tall, and they can only be tall like that if there's an internal structure holding them up. That internal structure is provided by a series of wall faces that are built into the cairn. We're now familiar with the idea of the existence of those wall faces and of their projection out into the cairn surface from examples in France, in Ireland, a highly contentious example, in Scotland, where we have some very elaborate, this is a wonderful piece of engineering in Drystone material at Quantoness. And indeed, you can see them here on the left at, that's Camsterlong, I think, and that there, I think, is Point of Cot, dug by some idiot some years ago. Here's a cairn that I dug recently, or operated on recently, and at that side over there, you can probably see slightly disturbed wall faces coming down like that. This wall face here is the outer wall face of the structural element within which the chamber was formed, and we call that structural element the core cairn. Now, the wall faces and the court cairn are specifically built to particular angles and configurations to support the mass of loose material that constitutes the body of the cairn. The chamber inside is built according to a set of rules which we'll explore very shortly. But there are not enough chambered cairns in the United Kingdom for people to acquire the knowledge of how to do it, or to sustain that knowledge over a period of time. Now, of course, that observation is based in the first instance on the surviving chambered cairns. Throughout Europe, a consensus has emerged that only about 1 in 20 of the cairns that were built now survive to us. Willisoskis, in his book on European archaeology, gives a good summary of the evidential sources, of which the best one is the Danish source, which, because they gave tax relief on cairns and having a dolmen on your land, there are actually very good records of how many cairns there are. Their original counts were in something like 60,000, of which now only about 3,000 survived, the vast majority having been lost only in the past few centuries. Now, in the background of chambered cairn building, there's an unnoted vernacular building tradition of building field houses, shepherd's huts, the sort of things we think about in Scotland maybe as, you know, the transhumance buildings in the uplands, ephemeral stuff. This is far from ephemeral. But there are thousands, probably tens of thousands of these kinds of structures. In France, they're cabanes, in Italy, Trulli, in the Mediterranean, Navete, in Ireland, Clachoin. And the scale of this, you know, relatively low-grade building, unfortunately, these slides show very good examples. Most of the examples are far less elegant than these. The volume of these buildings, the number of them which were constructed and continue to be constructed to this day, is sufficient to sustain a knowledge of corbelling, of the management of compressive force on lintels and so on. And all of the tricks and traits that we see in prehistoric Drystone building, we can see in these modern vernacular examples. They're worthy of a lot more attention than they get, I'd have to say. Right, the kind of construction we see here, where you have lots of walls, which are just like what we see in the chambered cairns, is called in France, Moors call it Polycope or Polycope walls. And this terminology implies, in one sense, that the entire structure should be considered as a single but complex wall, and that's not a bad way to think about it. It's a wall with many wall heads or copes. The coping stones are the top stones on a wall, so polycope means many-topped wall. And this is the terminology which I've adopted for looking at cairns in Scotland. Cairns without internal structure are known. The closest cairn to the one I've just showed you on Warehouse Hill it has no internal structure. It probably was a very early Neolithic cairn with a simple megalithic kist in the middle of it. That was dug out about 700 AD, according to the radiocarbon dates, and a long kist was put in. And interestingly, that long kist looks down over the broch at the foot of that hill. But it did start life, I think, in the Neolithic. I have no evidence to prove that. But we have the remnants of a megalithic kist inside this unstructured mound of stone. Okay, let us turn without further ado to something else. The process of forming a chamber, something else is chambers, we're going to have a wee look at them. Forming a chamber is a process of defining a space using walls which are more or less upright and then somehow roofing over the contained volume. We'll begin our review of chambers by examining walls, or more commonly wall faces. The simplest chambers are megalithic in the strict sense, which is that they're built of very large stones. Corbelled structures are built of very large numbers of relatively small stones. But megaliths in that strict sense ensure their stability, or their builders try to ensure their stability, by setting the walls upright in trenches or within excavated volumes of natural hillside or hills for that matter, entire hills for that matter. The orthostatics are upright slabs. An orthostat is an upright slab. Usually it's earth fast, it's set into the earth, but that's not necessary. Some of them sit on top. The orthostats can be very large indeed, and some of these were quarried and surface dressed. And these examples from Malta, from a Maltese temple, are said to weigh several hundred tons. I saw one there that I think weighed more than 100 tons. But as recent banking scandals have revealed, the Maltese grasp on numerology may be slight. These hewn granite slabs form dolmens on the Spanish side of the border with Portugal, and they're scarcely less massive, as the presence of the ladies will show. These are Anne, who is in that further slide over there. Anne and I use each other as BSSSs, which is British Standard Spousal Scales, for photographic purposes. Someday we'll have to work out what the ratio is of her height to mine so that we can give a calibration for cross comparisons. Anyhow, the three illustrated Spanish granitoid dolmens form part of a series of, or a long string of cemeteries down the Spanish-Portuguese border, mostly on the Spanish side, southwest of Madrid. They're remarkable for their consistency of form. The form is illustrated by the little blue rectangles. Is that blue? By those rectangles at the top there. They always have a really massive, large slab at the back end. And then the sides are formed of three overlapping slabs. That process of overlapping is called imbrication. And what happens with imbrication is that instead of having slabs that can abut each other but can slip past each other, you have slabs that overlap. They can't move that way, and the surface friction between them in that plane keeps them very, very steady. All of these are inclined. The sides are inclined all the way around. They're brought to a common height, and a flat slab is placed on top of them. At the front end, you have two radiating, again, pretty massive slabs well set into the ground, along which, as you can see here, the final slab is pushed along. It slides along those slabs up under the lid, which, or the capstone, which is already in place. And they often have a little letterbox-like opening cut there that straddles that bridges the gap made by these two stones running in here. Presumably that letterbox-shaped opening is used for accessing the chamber after an initial period of burial, or I guess. My feeling is that it's put there so that the guy who's inside, encouraging that stone up against the two sides, is able to get out of the chamber. Which way or whatever, there it is. Now, you saw that they're pretty big, even at this scale. They range from about 1 meter high to about 3 meters high in the examples that I have photographed. But the biggest of all, it doesn't light up like that. The biggest of all is this Dominic la Cara, where that stone is over 7 meters high. It's an enormous chamber, but it's built absolutely canonically. It has that very big backstone, which is actually there and broken off at about that height. And it has the 3 side stones, each of them imbricated. And at the front, however, something different happens. Because of the size of the chamber, the containing mound has to be bigger. And so you can't have access to the front face of the chamber. So they've had to build a passage. You know, the ordinary dolmens do not have passages other than ones you can crawl on your belly through that letterbox into the interior, but they don't have structural passages that intersect with the chamber. This is very massively built. It's enormous. You can walk through it standing up. It's about that high. That's the BSSS plus 20 centimeters maybe. But on the innermost capstone, which is particularly massive, they've ground a slot across the inner edge of it. And that slot, I think, seated the closing slab on the front face of this dolmen. So they've preserved the idea of how they manipulate the structure. They can only do it once, of course, because it's going to be buried under about 10 meters of soil and stone. But they have preserved the basic idea. I wanted to invite you into this monument, as it might be, for the purposes of explaining or of realizing that monuments are not infinitely scalable. When we try to scale, particularly Drystone monuments, we very quickly run into big problems of structural stability. Here we have a problem of organization, which requires a different format. So the message is, some monuments are scalable, but the scalability may be within certain limits. And some formal changes are driven by the attempt to make something beyond the scale that its fundamental design can accommodate. Here's a source of change which didn't require the building to bunk. Okay, I want to talk now about canonicity, monumentalization, or aggrandizement, or something else. The chambers of the Iberian dolmens are highly canonical in form, but variable in scale over an order of magnitude. The largest in vertical linear measurement is 7 times higher than the smallest. The 7-fold enlargement in linear scale does not imply a 7-fold enlargement in all the other parameters because of something called the power law. I demonstrate here my incredible skills as a draftsman. If we take the bottom line, we have a modulus there which is 1 meter long, we'll say, and this one is 2 meters long. A 1 meter line will map to a 1 square meter area and to a 1 cubic meter volume. But if we double it, make that 2 meters, then we have not 2 square meters, but 4, and not 2 cubic meters, but 8. So every time we double a linear measurement, we increase the volume 8-fold. So the cost of going big in megalithic building is extraordinary. A structure that requires, as in the case of this la Cara dolmen, requires 2 or 3 orders of magnitude more effort in construction, cannot have come from the same social context as one that required only 1 order of magnitude. It's argued, therefore, it seems to me credible, that the scale range of the monuments, of this group of monuments, is evidence of social differentiation, with smaller, more resource-poor social groups creating the smaller models, and larger, more resource-rich social groups creating the larger. It doesn't mean that the smallest were first and the largest were last in some sort of evolutionary stepping stone thing. And it doesn't require that the monuments underwent a monumentalization or an aggrandizing process. It's simply a reflection of the resources that communities felt it was appropriate to dedicate to this activity, and whose opportunity cost, the cost of not using that effort to do whatever it was traditionally doing or whatever else you wished to do, that opportunity cost was also borne. Finally, then, we can say that the dolmen de la Cara was the unintended consequence of re-engineering a canonical form at a larger scale. And we'll return to that issue of scale variance anon. In building these megaliths in this Spanish group, you can see the landscape here. That's a house there. So these are enormous granite towers. And what they've done is to chop off the upper surfaces of towers. The outer surface of each of these slabs is rounded and weathered because it's come from the outside of one of these. And the inner surface is crystalline, crisp. It's been plucked away from the body of the stone. From the edges of some of the more complete slabs, you get a hint as to how they did it. I think they cut a groove around the top of a tower, created, to give the size of slab they needed. And then somehow they got in under the thing and prized it off the surface. I have no idea how they would have done that. It is said that if you light a great big fire on top of a granite tower and let it roast the stone for however long, days maybe, a day, a long period of time, and then you pour water on it, that the surface will come off. I've never seen it done. I've often read accounts by people who've also never seen it done. But that doesn't diminish its popularity as an explanatory mechanism. it's a bit of a mystery. Clearly there has to be a methodology. And I suspect that somewhere there's a little farmer up the back of a hill somewhere in Spain who's still doing it, whatever it is. Yes, anyhow. The Iberian, bear with me for a moment. I've kind of given up on that, yes. Okay, the Neolithic builder's mastery of cutting and shaping stone is probably most clearly demonstrated not in the dolmens, although technically I think they're a very interesting challenge, but really in the great tombs, of which the best examples are near Antequera. This is Menga, which is probably Europe's largest megalithic structure. And I mean, there's a person in there somewhere. There's a person there. Look. Not a BSSS person, but a slightly short European standard person. But these are enormous spaces, absolutely enormous. I think you could park a car in there, no problem. In contrast, Viveira is also a huge undertaking, but it's much more geometrically controlled, far more rectilinear in its composition and execution. The side slabs abut each other with great precision. I think they've been ground against each other to achieve that. The roofing slabs, again, are massive. And here they've pushed the roofing slabs way out. If these are the side slabs, the roofing slabs are way out here. And the reason for that is, if you put a slab of stone across here, it wants to break in the middle. If you have a big lump of slab out at each end, it kind of counterbalances the internal stresses, and so it reduces the moment of bending at the middle of the stone. These slabs are also surface dressed with little ground-in cup marks, dozens of them, and they use this kind of porthole type entrance to the burial chamber at the back end, and these are very redolent of the Maltese style of building we see in Maltese temples. There are 3 known and a 4th rumoured massive tomb structure at Antequera overlooking a big flat, wide, flat, fertile plain. Sadly, they're actually positioned in the middle of an industrial estate, and you have to cross a motorway on foot to get to see them. But, it's worth it. It's worth the risk. Here, however, they have this hill in the background, which is called Peña de los Enamorados. And you know that in contemporary Scottish archaeological literature, it's common to assert that monuments are orientated at features in the landscape. I very often can't find the features in the landscape, but that's probably because I'm stupid. This landscape feature, however, is the most anthropomorphic one I've ever seen. I think it genuinely looks like a human face. I'm prepared to buy this package. I'll turn now, on that happy note, to the North European Atlantic zone, the dolmen-like passage graves, which were built in Denmark in split or unsplit granite or granitoid boulders. Work in Denmark over the past 2 decades exemplifies a standardized, highly standardized Neolithic building process. Firstly, a trench was dug around around the circuit of the chamber, which is usually pretty parallel-sided with rounded ends. Same for the passage. And the stones were set up either in or alongside that trench. And then packed around the feet of the stone, you have this deposit of broken flint. Torben Dean tells me that they have up to 300 tons of broken flint around some of these chambers. Broken flint, some of which they have clearly roasted and then quenched because they're shattered, and you can see heat damage on flint in a way that you can't see it on granite, for example. Yes, the broken flint, the shattered flint, is amorphous. It breaks in all sorts of different shapes and sizes, and it has lots and lots of very sharp edges, which when you put it all together, locks together really rigidly. This is a wonderful foundation material. It forms a very rigid collar around the base of the chamber, and stops these even egg-shaped orthostats from shifting or from twisting, which is what would happen very easily if you simply put them in an earthen trench, revetted with earth. So this is an inspired little piece of engineering. Now, we'll return to it. Okay. The boulders that make up the chamber and passage can be oval, egg-shaped, or irregular, and in the chamber they're set up along the line of that trench and all tilted inwards, which you'll see shortly. You can sort of see it there. So that if their bases are kept slightly further apart from each other, then when we tilt them in, their heads will meet and lock together to form a sort of a ring beam that consolidates the monument. And with the feet firmly held in place by this flint underpinning, we create a very rigid structure, which may be why 60,000 of them survived up to the medieval period. Finally, a bank of shattered flint is piled up against the back. And oh yes, this is looking inside the monument. You can see how the stones lean inwards and are kept that way by the fact that their upper corners meet, or where they don't meet, that they're packed, the gap is packed with these pinning stones. I'll draw your attention, if I may, to the fact that the wall head comes to a certain height throughout here, and then above it you have what the Danes call the intermediate layer, which is made up of large blocks that run back out into the body of the cairn. The intermediate layer is invariably present, and it raises the height of the cairn. I guess it's a substitute for corbelling, which might have been easier to achieve, but this is really standardized building. Oh, next one. Those panels of pinnings, which can exist from ground level to the top of the gap between adjacent stones, either as a continuous gap or as two gaps, a bottom one and a top one. The pinnings in those gaps have between each pair of stones pads of birch bark, which have been soaked in tree resin. These guys definitely did not want the stones to move. Okay, they effectively epoxy resined them into position. This is such wonderful engineering. I just love it to bits. Okay, we've got over that. Now, while we contemplate this image here, let me say that Torben Dean, who leads in a lot of this work, and his colleagues argue that the purpose of the consolidation of the orthostats and their pinnings, and the use of layers of birch bark in the pinnings, and the use of layers of clay and topsoil sealing off the roof, and you see that here. I think that's clay, and that's the ground surface up there. And in here, in this example, there's also a clay layer inserted on the floor. They argue that the purpose of this is to create an eternal home for the dead. And you have to admit that if that was the interpretation, they've come blinking close to achieving it. Now, within the chambers, the ends, one stone, this is not my drawing. It's almost as good as my drawing, but it's not. But the end stone is usually, one end stone is usually omitted throughout the whole of the building program. And a gap is left through the cairn back here for access to the building site as the construction project goes forward. When they get to the when they've inserted that intermediate layer so that they have the uprights forming the chamber, and then they have this flat, very, very heavy granite lumps forming that intermediate layer in place, and the earthen mound in which it's all enclosed together with its layers of clay, if they're in use in the construction of the mound itself. When those are all in place, very large granite boulders. I have to say, I think there's a little bit of a scale problem here. I think that they're not quite that large. But they are then brought onto that flat working surface. And it's very clear that a working surface is created and then the roof is placed on top of it. Finally, that end slab is put into place and sealed in place, and the end of the cairn is finished off and earth is mounded up over it to give a complete monument. This is Neolithic engineering, how it should be done. Like so many other things that the Danes do, they did it awfully well. Now I wanted to look at a cairn from Assynt in the northwest of Scotland that I dug. This is a cairn called Borrowland East. It's beside Borrowland Loch, which is just south of Assynt Loch, or Loch Assynt. And it's formed in what is a cyanitic type of the local granitoid complex, which is part of the Moyne series of geological deposits in this area. The chamber here is formed from thick angular slabs, and it's interspersed with panels of pinnings. And the whole is overlain with two courses of long but relatively thin granite sort of prisms. They taper from a front down to a back out in the cairn. They're hard to see here, I think, but they do exist in here. In some places we have 3 of those in because they're just not that they're not that massive. They're not as massive as the Danish equivalents that we've been looking at. But there is a distinct and a discrete intermediate layer, intermediate build in these things. Now, our scheduled monument consent didn't allow us to pull out a slab and sample it to see whether or not there had been tree resin in there, or even tree tar, and I regret that. Maybe someday we can convince them to let us go back and do it. The end stone as well, which is over here, is distinctly different from the other stones in the chamber because it's a very, very large, fairly thin, 20 centimeters thick slab, trapezoidal in shape and leaning well back into the space behind it. And part of the reason why it's leaning well back is that the material behind it was not very well packed. And it looks as if there's a passage out the back of that, out behind that backstone, through which builders could access the chamber. By now, I guess you'll see where I'm going with this. Here's some other pretty pictures. These are laser scan images, and they're very useful because metrically they're very precise, but visually they're not the most rewarding. That's that backstone. There's the entrance opposite it. And here's the working surface up here, look. At the top of the intermediate layer. It will be clear without further elaboration of detail that Borrowland East was built in a fashion that would not have surprised a Danish Hoy builder. I'm not much given to long-range connections in prehistory, and I wonder to what extent, and I have wondered to what extent, working with intractable material like granite constrains the builder's freedoms of choices, constrains them in ways that foster convergent solutions to structural problems. John Ruskin, him of the Stones of Venice, in his, I can't remember how many pillars of architecture he had, 7 was it? 9? 7. Thank you. He distinguished between architecture, which he said was all the elements of a building that you didn't need. There were the bits that were not engaged in structural stability. And all the rest he called building. We would call it engineering now. The intermediate zone at Borland East is not a requirement, I beg your pardon. The intermediate zone is not a requirement of the structure, and if greater height were desirable, it could have been provided by Corbelling. The use of that intermediate zone construction is a bit odd. We don't have other things like that. We don't have lots of other things like that in the Scottish megalithic calendar. And so it seems to me that that's a cultural choice. That's architecture. It's not just engineering. And therefore, I conclude that Borland's builders had at least seen Danish construction methods or spoken to Danish megalith constructors. Whether that was in Denmark or elsewhere, I don't know. But these do not, I find it very hard to shoehorn these into the paradigmatic assumption that all of our megalithic inspiration comes from Spain, Portugal, and France. I think we were getting a lot of it across the North Sea here. Right. The cairn at Borland, we're standing on the working surface and looking down the slope, and there's a wall face there, and there's one running through there as well. And this is a Polycope wall. It's hard to photograph this stuff because grey stone flattens out against grey stone when you photograph it. There are people who can do that very cleverly. I'm not one of them. It was a D-shaped cairn here, and its facade would have looked like that. It had, we thought originally, possibly a long cairn attached to the back of it. That's the monument, which is a pretty undistinguished hump on a hillock. But what we discovered was, we discovered that that was not true. There isn't a long cairn attached, and I'll explain why in a moment. This is the interior of the cairn, just quickly to give you an image of it. Here's our intermediate zone here. This is debris piled on top up here. And these are very long, spiky prisms of granite sticking out the back. Here's our very nice packing, with or without resin. And here's the backstone that I spoke about. You can see that that's massively, disproportionately large to the rest of them. The surfaces of these stones had been dressed. You can see these little scallops. I say you can see them, I hope you can. I'm finding it hard to see them, which have been detached from the surface. And some of the stones had also been almost like flint napping, brought to shape. There's a percussion point there, and that's one of those, conchoidal fractures there. And here there's a concussion point, and then this long splinter had broken off it, I think, but somebody worked the thing to shape. It's not a rough piece of stone picked up and put in. It was quarried and brought to the desired shape. And I think this is the material that they used for it. I had dumped most of the lumps of this material in the waste boil, in the spoil tip rather, as waste. It's extraordinarily heavy. It's a form of quartzite that has been re-metamorphosed. Quartzite on its own is metamorphic anyhow. It's been re-metamorphosed. It's extraordinarily dense, extraordinarily heavy, and very, very hard. I did have a go at with just a lump of it from the topsoil at some of the granite exposures on the hillside, and it's quite effective. Excuse me. It was quite effective at chopping off lumps of granite. And, I hope that someday we'll get the opportunity to experiment properly up there and come to a better understanding of how this stuff was worked. Inside the passage, there's a rocky boss in the floor, which appeared just as a rocky boss, but when we finally cleaned it up and got the mud out of it, you can see that it's been quarried. By looking at the sort of geometry of that boss, it seems to me that it stood about 35 or 40 centimeters high up in the chamber floor, and they've just chopped it out. They have cut it out. They also quarried away the bedrock behind that back stone. The bedrock was high, and we then realized that what we thought was a long cairn was really the extension of this crag and tail feature. When a glacier had moved along the hillside, it met a strong resistant lump of rock, and it wrapped around it, leaving that rock as a steep-sided promontory. And then fading out behind that rock, it then tailed away, grinding down the bedrock behind it, but still leaving it higher than the rest of the surviving hill. So this is a crag and tail. Probably the world's most famous crag and tail is here in Edinburgh, and it runs from the castle, which is on the high rocky eminence, down the high street to the palace at the bottom end. Those are crag and tails. The sculpting of bedrock in pursuit of architectural aims is not uncommon. It's not as uncommon in Neolithic architecture and archaeology as we can imagine. This is a French Chris Scarry's excavations at Prissé, and you can see that in the front here they have actually, you can probably see in the front here, they've sculpted away the bedrock to make extra steps for the side of the cairn. You know how the side of the cairn is polycope? They've sculpted the hill below to increase the sort of presence of the side of the monument there. Now, before turning to this kind of chamber building, I want to just make a quick observation on chamber floor deposits. They often provide a wealth of information. You can see that, for example, in Quanternesse, where Renfrew uncovered masses of human remains intermixed with animal bones and God knows what all else. But none of this, of course, relates unambiguously to the construction of the cairn. And in the absence of structural detail, we have to rely only on art historical narratives of the enclosed materials, even for relative chronologies of the chambered cairns. It's not unusual to cite guesses of construction dates based on the earliest date. Let's take the earliest date. It would say it was built the year before. That's science, I guess. Bayesian analysis is sometimes used to massage the radiocarbon dates into narratives that we find easier to live with. And certainly Bayesian reworking of Severn Cotswold tomb dates have created some interesting narratives. I'm alarmed, however, at the ease with which we, the rest of us in archaeology, have simply uncritically taken Bayesian outputs as if they're truth. You know, they're not. I'll come back to this later, but I just wanted to make the point here that the container is not dated by its contents. You know, you have to have the purse before you can put your money in it. Now I'm going to turn to Drystone building and wipe that out fairly quickly. This is the site of El Romero, which has a wonderful corbelled top to it. There's the entrance down there. Long, long entrance passage built in the same style as Menga and Viveira, but the chamber and the roof is built in Corbelling. Let's look then at Corbelling. Let me go back for 1 minute. Let's hang on for 1 minute and just have a little delay here in that here's the chamber and here's a passage that has to go into it. The chamber is built within its core cairn. It's very massively built. It's very, very heavy, and we have to put a hole through the bottom of it. That applies enormous pressures that would easily break the ordinary lintels with which we cover the passage. Not only that, but because there's a gap in the tholos, which relies on its continuity for its stability, the sides of the tholos are, the tholos that form the sides of that gap, they're free to move in now. And when that happens, it'll destabilize the whole structure. So a huge amount of Scottish Drystone engineering relates really to that junction there. And you can see that where we have extraordinary pressures in Newgrange in Ireland here, they have used extraordinarily large lintels. But those lintels are not supported on the passage uprights. They're supported on the cairn material outside. So they're bridging structures within which you can have a sort of fancy pants. It's mimicked, in fact, in concrete here in the modern relieving structure that was put in during conservation when I was a child. Corbelling relies on the fact that the cobblestones are tilted slightly upwards. And when that happens, they prop each other up. And they can't fall down. I mean, they're stable unless either we crush the edges of the stones here, say. If these edges become crushed where they meet, then that becomes a looser ring and the stones are free to fall. Or one of these stones is pulled out, in which case the circumferential forces are free to expand what's left and to make the whole thing fall down. One way of dealing with that is to put in orthostats, as we have, say, here. And in between the orthostats, we put shallow arcs of walling. Again, properly linteled. And they provide enormous resistance to the mass of the cairn outside, and their lateral forces are checked by the orthostats. And of course, if we have, say as here, if we have pressures going this way, and on this side pressures going that way, and they meet at the orthostats, in fact they cancel out, and we're left really with residual pressures at each end. And the question that strikes my mind is this, is that why we have blocks of masonry built outside the chamber here, and of course at the back end, the unresolved side force is prevented from pushing out the back end of the chamber by the bulk of the long cairn back here. In addition to these masonry blocks, a block of masonry, a built solid mass of masonry at the front here, they're augmented sometimes, in fact relatively commonly I think now, with just huge big lumps of stone that are handy, that they haven't used in the building. They stick them in there and it helps to rivet the cairn against what's going on. To rivet against the pressure of the tholos, or, to help with managing the tholos and stop it from spreading, one solution, which we see in Campster Round cairn, is to put in two enormous orthostats there to build the tholos up against the back edge of them, and then to prop them apart with these stone blocks so that they resist the attempt of the chamber to fold in on itself. That's one solution. Okay. I'm going to come back. I want to use those just to illustrate the challenge of building chambered cairns, which all boils down to how the devil you get into the chamber. And I'll show you in the next lecture that that's what underpins the variations that we see in Scottish architecture, Scottish Neolithic architecture. It's possible to do a partial corbelling, as here, and to finish the roof in wood, and that was a common Mediterranean approach. In Scotland, we've never really had good quality wood, same as we still don't have good quality wood, and so we didn't seem to do this to any great extent. Here's the principle of corbelling in brief. the downward force exerted by that mass out there must be equal to or preferably less than the downward force exerted by that mass in there. Otherwise, from that point, that mass will fall in. I've now built something getting up towards about 100 of these with different vertical sections and in different lithologies, and the rule works. It has to. It's just basic physics. It's worked out obviously in the first instance by rule of thumb by Neolithic builders, and they could take liberties with it and make the outer wall very, very thick. But what's the limit? So they could easily, you can be a sloppy corbler if you build very thick walls. But I want to show you that if you simply double the width of that chamber there, and imagine it's 10 meters long, for an increase in volume of 5 cubic meters in the chamber, your price is 1,200 cubic meters of cairn. So the cost of making something bigger, is high. And I think that is what forces people to optimize their designs, because most of the Neolithic cairns are built very close to the limiting conditions for stability. They didn't need to know the mathematics underlying that stability. Experience brought them as close to it as they dared. Treasury of Atreus, largest unsupported roof in Europe for something like 1,200 years, still standing. It's not until the Romans invented concrete domes that this was surpassed. This is contained within a cylindrical hole cut through a hillside, so the hill itself is what's providing support against the lateral forces. Sorry. In all cairns, in all chambers rather, all chambers are built within their own supporting cairn, which I've called a core cairn. You can't build a chamber without a core cairn. It has to be there. In fact, the chamber is just the inner wall face of the core cairn. The rest of the intramural or intra-cairn walls are built in proportion to the ambitions of the builders. The bigger you want to make the monument, particularly the taller you want to make the monument, the more of those walls you have to put in. Again, it's possible to provide an analytical understanding of that, but the pragmatics of it would have been a steady teacher. If you got it wrong, it fell down and killed you, and so you didn't get it wrong again. If only education could move in that direction. I'm going to just pass that. That cantilevering effect that was in the last sketch is where you have the lintel that goes out over the edges, and the weight there is pushing down and sort of providing some uplift against the weight that's pushing down there across the major span. I think that may be what's being done in this group of cairns in Ireland called the Carrowkeel cairns. I have some blurry photographs of them, and I did spend a day rambling around them. But I'm not confident enough to assert firmly that these guys are using cantilevering rather than corbelling to achieve their roofs. But I think that's what they're doing. And will this work? Yeah, oh, it worked very well. Let me just, there we go. This is a cairn. Observe this, and I'll just make a final comment on it.
memory on my camera. I've got 36 seconds. Fine.
Sorry, I skipped past a fly-through of a laser scan of a full-size chamber that we built. We then used it to experiment on what happens to material on the chamber floor when the walls collapse in. To make the walls collapse, all we have to do is take material away from the back. That's what I was doing behind the picture there. And the thing teeters. That was, 2.5 tons of stone, playing rock and roll on the wall head there. And the value of some of this work lies in the fact that we begin to understand why, for example, material that we can show that material that was on that chamber floor ended up to 40 centimeters up in the debris that fell off and crushed it. And that really, I think, is where I should stop for today. And we'll carry on from there in the next lecture if you have the patience for it. Thank you.